It's fundamental. And sometimes using statistics, we have nobody saying they never use statistics, which is really interesting because we did have a couple of people who don't code, but they're probably using other types of CAN software or Excel or something to do some type of statistics. Okay, we respect that. That's very important. All right, this was really helpful. Thank you very much for sharing. That helps us understand the group. If this was a small group, we would do a round and we'd hear more about you. I apologize. We can't do that in an hour. you'd feel a little cheated. You like showed up here, booked the time, and all we did was introduce ourselves. Would not be great. What's the goal today? Well, we want to give you some concepts. We want to give you new skills, some new ideas, demystify and demonstrate. That's our goal. That's what we think we can do. It is a sprint, full steam to mineral mining, machine learning in an hour. We can't claim to cover everything, but we'll do it kind of quickly. Why mineral and mining? Why do we want to deal with that problem? Sparse data, spatial, multivariate, heterogeneous, high value decisions. You know what's very interesting? That's analogous to oil and gas. It's very, very similar in application. It's got some distinctly different problems, but we recognize that these types of subsurface machine learning problems are critical and we can do a lot of powerful things with machine learning here. What are we going to do today? Our model. We have a mine that it's multivariate, multi-feature. We have multiple mineral concentrations, zinc, iron, and lead. Not atypical. In fact, the data set you'll see is actually shaped based on another published data set. I didn't have that data set, but what I did, I'm a geostats person. I made a reasonable data set, put in some constraints, and I got something quite reasonable. We're going to demonstrate prediction, data imputation. What is that? You have missing grades. Not atypical. You could have couple of grades measured and you're missing another grade, you need to re-estimate it. We'll show you how to do that. That's our model to get the missing zinc grade. Data QC. I hope you can see we can flip this model on its head. We can ask the question, what would we predict from iron and lead concentrations, percentage volumes? Therefore, what should we expect for zinc? And if zinc is outside of that region, there's something going on wrong here. That's a data QC idea, and it can be purely inferential. What does that mean? Building a model to understand the shape, the form, the population, the sense of the relationships, and so forth. That's very powerful too. Okay, let's talk about data analytics and machine learning. Jumping right into it. What is machine learning? Well, we Google search it just like everybody else does, and we land on Wikipedia, the Wikipedia page. If you read the definition for machine learning, is a study of algorithms, mathematical models. I'm just making sure I got the chat window open here, because if anybody has a comment, feel free to go anytime in the chat window. I'll get the participant window here opened up for sure, so you can raise your hand, jump in anytime. It's a study of algorithms and mathematical models. Okay, it's not one model, it's a toolkit of models that computer systems use to progressively improve their performance, learning. These are learning algorithms, toolkit of learning algorithms. On specific task, to build a mathematical model of sample data known as training data. It's learning from training data, that's good. In order to make predictions and decisions without being explicitly programmed to perform that task. It's general. It can work on a wide range of problems. Okay, so toolkit of learning, they're training on data, and they're general. They'll work on many problems. Now, if you read right to the end of the article, you're going to find an important statement where it is infeasible to develop an algorithm of specific instructions for performing that task. In other words, not a panacea solution. If you know the physics, if you have a great geologic interpretation or relationship, or the geologic physics from the depositional processes or the alterations in the mineral sense, use that information. Don't jump to data-driven approaches if you understand the system. All right, let's talk about variables and features. Very quick definitions. This is going to be rapid fire, and then we're going to jump into machine learning. Feature, any property measured, observed in a study. Now, if we're talking about mining, mineral grade is pretty common. The scale of the measurements, that's important. That can be variable. And we'll find that things will change over different scales. Mineralization type, how was there alterations? Is it primary, secondary? The geometry and orientations are also very important. Impurities can be a detriment or an issue. Trends, information about non-stationarities or changes are important. Rock hardness, diggability. How do we extract it? How do we mill it? These are all geomechanical properties of the rock. These are all features that we could be working with. Now, Fatima, you had asked the question. Oh, Avi, you responded. Thank you very much. You're on the job. Perfect. Thank you. This is an example right here from the Irish University Rocks. Very nice virtual microscope online. And an example right here of nickel ore. And you can just get a sense that we all know that the features are complicated. And in fact, may I argue, require significant analysis and interpretation. We can't just say, oh, I'll just measure it with a tool. We have to actually look and do interpretation of the rock types, the type of mineralization, and so forth. We don't just sample from drill holes and say, we'll just put the data in the model. We need geologic and engineering knowledge. The machine learning nuts and bolts. What does machine learning look like? This right here, my friends, is a machine learning model. That's how simple it is. The model F is representing the natural system. It's trying to take the predictor features, which are the model inputs, X1 through XM, and it's trying to get an output, the response feature right here. Now, whenever we build these models, we acknowledge that there will be mismatch. In fact, and I'll show you right away, if you don't want mismatch, you're overfit. Your model will have no ability to generalize away from the known data. It will not predict well. So we're going to acknowledge that we have some error. Machine learning is all about estimating this model F for two purposes, inferential and prediction. Let me cover those. Prediction. Prediction is all about estimating this function F. So in other words, I put F hat. We don't have the natural setting, not all of it. We have an estimate of the natural setting, a abstraction, a model of it. It takes the inputs and it tries to estimate the response feature. We are focused at getting the most accurate estimate of the response. That's the idea of prediction. Now, if you're stuck, if this doesn't make sense to you, let's go back to traditional statistics. Predictive statistics are the following. Given an assumption about the population, our model, predict the outcome of the next sample. That's a great way to think about prediction. In other words, I'm going to drill another drill hole. I want to do some type of pre-drilling type of analysis or prediction. That's what my model is going to do. It's going to say, I expect this grade in this block before I mine it, or before I send it to the run of mine pile. This is what I expect the grade to be. Or maybe if we're talking about the run of mine pile, now we're talking about aggregation. And as we change the scale, this is how we believe the grades will homogenize, so the rock properties. So that's what it's all about. Now, if you want a very simple example, given a fair coin, what is the probability of 7 tails and 3 heads? That would be a prediction problem. You see, the assumption about the population would be the coin is fair. Okay. Now let's talk about parametric and non-parametric models, because we got 2 ways we can build these models. Parametric models make an assumption about the functional form or shape of F. Now that's really good because you gain a lot of simplicity, the advantage of having only a few parameters to work with. Here's an example, a very, very simple example. Anybody who's done basic modeling will recognize this as multilinear regression. We've got a bunch of coefficients being applied to different features, inputs, X1 through XM, and we've got a constant term right here. If you looked at the model over one predictor feature to the response, this is a model for nickel percent volume over depth. We're expecting maybe some type of alteration zone with a trend. I've seen this in nickel laterite type deposits. And so we're trying to look and see what's going on as far as this change or trend. Now, I want to show you something. There's a risk. When you build a parametric model, you made an assumption about the form or shape of the natural setting. The result is the natural setting could be very different. You see this? There's cycles here. But if you look at the model, clearly it's unable to capture that complexity. That's a risk with parametric models. Non-parametric models are different. And many people, when they think of machine learning, intuitively, they're thinking non-parametrically. What's the idea? You make no assumption about the functional form or shape of the natural setting, the relationship. It's more flexible. It learns the shape from the data. Less risk that F hat, the estimate of the natural setting, is a poor fit. But typically you need a lot more data. What do I like to say? I say non-parametric models, machine learning models, are actually parametric or parameter rich. It's very interesting because this is a decision tree. We're going to build a decision tree later. You can see it was able to learn the form of the natural setting with some abstraction. It's not perfect. But this value, this threshold, this value, this threshold, every one of those is a model parameter. 2, 4, 6, 8, 10, what do we have? 25, 30 or so parameters in this model. Now we look at the number of data. This is where I go back to my traditional statistics and I say, well, I'm thinking degrees of freedom. How many assumptions versus how much data do I have? And I can become concerned. Do I have enough data to support this model? Now, what I'm going to do is I'm going to show you for any type of machine learning model, how do we build a machine learning model on one slide? This is the entire workflow right here. What we're going to do is I go back to my problem of depth in Z or Z for my Canadians. This is depth versus nickel concentration. We have our available data. Now, what I've done is I've segmented the data into training and testing subsets, mutually exclusive, exhaustive. I'm going to take the testing data, the circles, and I'm going to hide it. You know that place in your office you rarely go, the papers are built up there and you really haven't looked at them for years? Hide them under there. You're not allowed to look at it. Okay, so you take that data out, you keep the training data. Then what you do with the training data is you fit. You're going to train model parameters and get a best fit model. This is linear regression right here. We move the model around with the slope and the intercept coefficients. This is a third order polynomial, more complicated. A fifth order polynomial, a seventh order polynomial. Now it's getting crazy. If you look at this carefully, you'll realize that what we've done is we fit a bunch of models to the training data, and the models were increasing in complexity. That complexity means flexibility, ability to fit the data. Do you see what's happened? By the time we get to this seventh order polynomial, we are fitting the data with almost no error at all. This is the error distribution right here. Now, we're fitting the data with almost no error at all. Now, as we go to simpler and simpler models, we have a poorer and poorer fit. But what we're going to do is we're going to check the error at the testing data. So remember that data that we hid, we're going to bring it back in. All right, I misspoke. This plot is the distribution of error over testing. If you look carefully, what you'll see is that the narrowest distribution, the lowest amount of error in withheld testing data was the third order polynomial right here. We pick that model. That is what's known as tuning the model hyperparameters to get the right degree of complexity and flexibility. Now, what's the problem? If we did not do that, if we pick the model that has the best fit with the training data, which one of these models would we pick? The first, the third, the fifth, or the seventh order polynomial? Anyone? In the chat window? Which one has the best fit with just the training data? Yeah, Stuart, I agree with you. 100% for that. Thank you very much, Glenn. Everybody, I appreciate that. The seventh order model would have the very best fit, but that model would perform very badly at new locations or with new data not included in the model fitting. In fact, I should apologize. I'm pretty sure the seventh order polynomial is punching a hole through your floorboards right now. Okay, it's a really bad model away from the data. That's what we're talking about. Now, I used a bunch of terms I got to define. Model parameters that we train with the training data. If you look at a third order polynomial, B3, B2, B1, and C are the model parameters. Okay, we change those, we can change the slope, the curvature, and so forth. So we can get the very best fit with the training data by changing these model parameters. Now, hyperparameters, I use that term too. We have a first order, third, fifth, seventh order model. The hyperparameter is anything that controls the complexity of the model. In fact, the choice of polynomial order is the hyperparameter. We tune the model hyperparameters with regard to the withheld testing data to avoid overfit. Now, Ibrahim has a really good question. What's the difference between testing and validation data sets? This workflow that I'm showing right here is known as the training and testing workflow. There is another workflow. There's more than one way to do this. It is a training, validation, testing workflow. It goes like this. The same thing I showed you, but what we do is we call the withheld data that's used to tune the model hyperparameters, we call that validation. And then we have another part of the data set that we withhold the entire time. That data set is then checked against the final trained and tuned, complexity tuned model. What's the idea? The idea is to have a part of the data to check the final model, and that data does nothing to change or update the model. And so people see that as a more rigorous workflow. I'm showing you the more simple train and test approach. Ibrahim, did that help you? I do appreciate the question. Thank you so much. All right, hyperparameter controls model complexity. I've had students get confused. Just ask yourself, if it controls fit, it's a parameter. If it controls complexity, it's a hyperparameter. Now, there's a very important concept here, and it's called the model variance bias trade-off. There's a wonderful explanation. There's derivations, James and all, and the more complete treatment too that came from has the full derivation. How does it go? At the end of the day, what I want to know is the performance of my model on data not used to make the model. Okay, so the testing data, let's say the testing data. So the expectation, statistical expectation, which is like a probability weighted average. Okay, so you can think average, that'll be fine, of the difference squared between the true values of the response, why not, at locations not used to train the model, versus the predictions of the model. You see F hat and all of the X's at that same location. This is the squared error in your model over testing. And this is the average squared error over testing. If you take this quadratic, expand and use the concept of statistical expectation, it will turn into 3 additive components. Okay, we've gone up a steep hill, but I hope you're still with me. The 3 components of error in our model are model variance, model bias, and irreducible error. This is very, very important. Model variance is error due to sensitivity in the data set. Now let's look at this plot. As we have a simple model, low complexity. We have a complicated model, high complexity, very flexible. What we should see is that model variance is low for a simple model and it increases. Let's think about that. If I have a linear regression model and I change the data, the model will move a little bit. If I have a 7th order polynomial and I change the data, it's going to whip around, really unstable. That's model variance. Okay, model bias is like the opposite. It is error due to using an approximative model. Remember the example of depth versus nickel grade. The linear regression model was too simple to capture the cycles. Okay, so a very simple model will tend to have higher model bias. More complicated models will reduce model bias. Irreducible error, we have to live with it. You can't escape it. It's error due to missing variables, limited samples. We don't measure all the features. We don't have the right accuracy in the measurements. That does not depend on the model. You add them all up and you get a measure of the performance of your model in testing. This is critical. Now let's look at that. Let's think about that. It turns out that if you do that, you'll get a curve like this. It'll come down as you increase model complexity, it'll go back up. Now, if you look at the error in training, I hope I can convince you that as you add complexity, your model fit, the average squared error over the training data, will go down and go down and go down. And at some point, you'll perfectly fit the data. That's this plot right here. The zone of model complexity, where you start to increase error in testing while training keeps going down, that's known as the zone of overfit. That's when your model's overfit, and that's why we have our workflow to avoid model overfit. What is model overfit? If you Google search it, it's fitting data noise, data idiosyncrasies. I've done demonstrations and shown the relationship between data quality, noise, and overfit. Increased complexity will generally decrease the error with regard to training, but testing will continue to go up. Overfit. Here's an example of an overfit model. You see that we perfectly fit the data. Here's a more balanced fit right here. Let me just mention SCIKIT-LEARN. Wonderful. I'm a big fan. Great. Library of inferential predictive machine learning methods. They have many. The only place I feel that SCIKIT-LEARN falls down, deep learning. I use it for everything up to random forest, gradient boosting, but after that, I go into other packages to do anything like deep learning, like convolutional neural nets or complicated artificial neural nets and so forth. It's well documented, robust code. It's got a uniform format implementation. What do I mean by that? The common steps with SCIKIT-LEARN: instantiate, make a model, set the hyperparameters, fit the model to the training data with that complexity, predict with the model, and there's all kinds of cross-validation, k-fold cross-validation, training test separation schemes. It loops over, it does all of this, checking model complexity. I'll show you that. It's very, very useful. Let me just, I'll just show you a I'm not going to talk about a simple machine this time. Let's talk about decision trees. If we had more time, we talk in more detail. There's a lot more we can talk about. Let's just start about segmenting the predictor feature space. Now, what we're going to do is we're going to try to take the predictor features. I'll show you examples with just two. Remember, we got lead and we've got iron, and those are our concentrations. We're going to try to make predictions of zinc. Why use two predictor features? So we can visualize it, so we can look at the model like this. What we're going to do is we're going to segment the space, and then we're going to use that segmentation model to make predictions. Let me show you how we're going to do it. How does it go? A decision tree tries to do this. It tries to split up the predictor feature space. Here's a one-dimensional example going back to nickel versus depth. We have regions. We've broken it up into region 1, 2, 3, and 4. Then what we do is we use the average of the response over that region. This value, this value, this value. You notice it's kind of stepped. It's going to be stepped. This is the fundamental idea of a decision tree. Now, how do we come up with the regions? We've got two predictor features here. We're trying to predict, once again, a grade right here. If you had all flexibility, if you look at this model right here, it would make perfect sense with this data to have a region like that, a region like that, a region like that. That would be a really good model. That you see, because I drew these curves so that we got the light red colored data, which are low grades, and we have the dark high grades all segmented nicely. Can I convince you to take that? Look at that. Now, can I convince you to use this? If I can convince you to sacrifice that flexibility of drawing those curves so nicely and instead use this type of model right here, you will now have a very simple hierarchical binary segmentation model that's very flexible, very compact. It's a decision tree. Let me show it to you. I'll show you how we make the decision tree. I'm going to go ahead and switch to some code because I think it's a lot more fun to show code when it comes to building these trees. All right, let me just find. Oh, there it is, and decision tree right here. Can you all see my code? Let me open up the chat window again. It disappeared from me. Okay, and good, there's chat window. I see there's some questions. Sorry, I haven't been watching the questions. And I think we captured that. Okay, thank you. I do appreciate it. Thanks for letting me know you can see the code. Font size is too small. Okay, we can handle that. Fatima, how are we doing now? Did we get it? All right, I hope that's, let me know if that font size is not big enough for you. We have this on the learning management system. It's an example of mining decision trees. Anybody who hasn't worked with Jupyter Notebooks before, I don't have enough time to talk about the basics of working with Jupyter Notebooks, but let me just say it's a great place to prototype and make a very nice workflow that has documentation and code. We'll go ahead and import our packages. I'm going to run this fresh right here. We're going to go ahead and import some functions. Now we're going to load a data set. I made a data set here that we can work with. It is, once again, zinc grade %, volume %, lead, and iron grade. We're going to do our imputation problem. Now, for educational purposes, I'm going to sprinkle random noise over the grade, the zinc grade, in order to emphasize the idea of overfit. I think it'll be very beneficial. Let's go ahead and look at our data set. The first 13 samples, these are grades in percentage, volume % right here, based on an analog actual mine with the correct distributions, correlations, and shapes, and so forth. Now we'll go ahead and take a look at the summary statistics. I do this every time I do machine learning. I want to look at the statistics, see what's going on. I'm QCing, I see if there's skew, is there multimodal, I'll look at distributions. I'm not going to do all of that. Correlations are right here. This is very useful. We got to make sure that there is some degree of correlation between the response and the predictors. Now, linear correlations are limited, but at least we should try to look at them. Here's correlation matrix, but I like to do this also. I like to look at matrix scatter plots, look for multimodal on the diagonal, look for heteroscedasticity on the scatter plots, look for outliers, look for nonlinear relationships. This will help us choose the methodology. Decision trees are quite flexible. We've got good data coverage. We should do pretty good. Now let's go ahead and set the features to work with. The notebooks are available on the learning management system. And so we'll be able to go ahead. You can check them out too there. Okay. Let's go ahead and separate the data into train and test split. And we'll go ahead and check the distributions. Now, Daniel, this is a very good question. Daniel asks about the use of 20% for test and 80% for train. It is a balancing act. If you look at meta studies that have looked at a wide variety of problems, typically somewhere between 15 to 30% withheld testing is very common. You don't usually see people go beyond that. K-fold cross-validation, quite commonly 5 folds, 4 folds, which would match that, 20%, 25%. What's the thinking? If you use too many data withheld in testing, you get poorer models, but you get a better assessment of the performance of the model. That's the balancing act. If you use too many data in training and not enough data in testing, you get better models, but you don't do a good job of assessing the performance of the model over a wide range of values. So there is a bit of a, it's a bit meta. It will depend on the problem, but typical rule of thumb is about 20%, 25%. Okay, we look at the distributions and make sure train and test is fair. Now, I want to also look at the scatter plot right here. Lead, iron versus zinc is the color. Here's the training, here's the testing. This is very good because now we can assess whether or not, okay, we have some values right here which look like they are training data that are not being tested. Maybe we are not testing the model very well in this region. We see there's very sparse. We could also look for the contrary case. Maybe this value right here is a bit of an extrapolation from what we had for training. We want to assess that. Let me just demonstrate very simply a linear regression model. It's nice because I can show you this line of code is instantiation. This line of code is fitting the model. And then this line of code is using our function to do predictions. So we've demonstrated SCIKIT-LEARN, the basic steps. We've done nothing to do hyperparameter tuning. It's linear regression. We have no hyperparameters. Okay, let's go ahead and do decision trees. This is the instantiation of a decision tree from Scikit-LEARN, the tree module. Decision tree regressor. We have hyperparameters, minimum number of samples per leaf, 5. The thinking there is that we're going to use the average value within each region. How many values data should we have in that region? One would not make a good average. That would not be reliable. If we go very small, we're going to have perhaps an overfit tree. Maximum depth will be the number of nested hierarchical decisions. That'll make a more complicated tree as we make it more and more complicated or complex. What we have here is we have the training data with the decision tree. You see the discrete nature of the regions. We predict what the average of the regions. Zinc grade is the color. The testing data is right here. I hope you can see immediately just from the cross-validation plot that we do a much worse job with the testing than we did with the training, and that makes sense. Now, let me just show you something really interesting here. We could go ahead and we could make it more complicated. This is probably getting carried away, but we could say we'll allow a minimum of 2 samples and we'll increase the number of layers to 7, number of the depth. So we go ahead and run that tree. Can you see the increase in complexity? Now, what's very interesting, if you were to look very carefully, you'd see we're reaching a region where our performance in testing is starting to fall apart. The wheels are falling off the wagon now. Okay, now this is not the way to do it. We shouldn't just trial and error it. Let's go ahead and we're going to go down here and we will run a bunch of decision trees with the number of regions from 2 to 200. And we're going to go ahead and look at them. Don't worry, we're not going to look at all of them. The first decision tree, 2 regions. You see how it's hierarchical now. First tree with 2 regions, next tree with 3 regions, the very best next split. The next split, you see how the tree is just splitting, and I'm not going to scroll through all of them because that would get a little bit carried away, but we can do a scatter plot. This is the scatter plot of the number of regions, the complexity of the tree versus the mean squared error in testing. This is the total error using the variance and bias trade-off. And you can see right here that we get the minimum amount of error with this level of complexity. Okay, I'm going to switch into a couple of comments around random forest, and then we'll come back and go back to code again, because I don't want to spend too much time on decision trees and miss the opportunity to talk about random forest. Let's go back to the slides here. Ensemble methods. Now, any questions or comments, please go ahead and jump in on the chat window. Use the Q&A section. We're happy to help out. Remember, we had an issue here, and the issue was we are concerned about the expected test mean squared error, this term right here, but we have 3 components of that error, which are the model variance, model bias, and irreducible error. I want to build a more complicated model. That's a good idea. More complicated models tend to have less model bias. They're able to better fit the data. The problem is that model variance is wrecking it for us. We need to find a way to reduce model variance. How do we reduce variance? It turns out that you can reduce variance by averaging. If you average, you will reduce variance directly. In fact, anybody who's taken fundamental statistics will recognize this right here. The variance of the mean is equal to the variance of the sample divided by the number that are being averaged. In other words, if I can turn my estimator into a bunch of estimates and then I average them to get the final estimate, I can reduce model variance. That's the fundamental idea right here. Okay, so we're going to do that. Let's accept that. We're going to do ensemble learning with a bunch of estimators. Here's the problem. How do we come up with multiple prediction models? Because that's what I need. I need F hat B coefficient, little b representing the index for multiple models. We need to train multiple models on multiple data sets. What's our paradox, our problem? We have access to only a single data set. the Y vector with the responses, the X1 vector, the XM vector, 2 through XM vector. We have only one data table to work with. Anybody here, show of hands, who's done the Bootstrap before? Anybody, or in the chat window, anybody used the Bootstrap before? One, Rodrigo, awesome. Anybody else? Aaron, cool. Glenn, I see that. Thank you very much, you all. I appreciate the feedback. You let me know if I've got it wrong, okay? Bootstrap. The Bootstrap approach goes like this. You assess the uncertainty in a sample statistic by repeated random sampling with replacement. When I teach it at the university, I take a cowboy hat and I fill it up with 3 red balls and 2 green balls. And I have a student just come and sample with replacement 5 times. Then they count and get the proportion of red balls. And then they repeat, repeat, repeat. If you take the distribution of all of those sampled proportions, that gives you the uncertainty in the proportion of red balls. You see how simple it is? The reason we call it Bootstrap is it's the old English saying of pulling yourself up from your bootstraps. It seems like we're doing the same thing here. We're getting uncertainty in the sample statistic from the sample by repeated resampling with replacement. Okay, what are we going to do? We're going to apply the Bootstrap to obtain new data sets. We can do that. We'll take the data table. We have n data. We'll sample n times with replacement. You'll get a new data set. Why is it new? Because we did with replacement, which means that we're going to have more than one time we sample a specific value, and some values will be left out. Now we have a B data set, Bootstrap resampled. Then we're going to have multiple data sets, little b equals 1 through big B, and we can build a prediction model, F hat B, for each one of those data sets. Now we can go ahead and calculate predictions over each one of those data sets. We're going to build a model for each, make predictions, and now we can pool the predictions. This will attack our model variance. So reduce model variance, allow us to build a more complicated model and with low model bias, and we'll be much better off. Okay, so our estimator will now be the average of all of those Bootstrap estimates. That's it. Now, if you're wondering how to do classification, not a big deal. If you have a classification problem, you're trying to predict a category. 1, 2, 3, sandstone, boundstone, wacky stone, whatever it is, breccia, a rock type or something. What you're going to do is you'll just use a majority rule. You'll look at all of the classification predictions of a category over all of the B's, and you'll take the one that has the majority. Okay, not a big deal. Let's talk about tree bagging. We're going to use Bootstrap. How does it work? We're going to be able to reduce model variance as expected. We can grow the trees to be more complicated. Why? Because the approach of ensemble learning will take care of or help us with overfit. So we can grow the trees to be more complicated now. Now, this is a very interesting fact. It turns out that when we do Bootstrap, statistically speaking, in expectation, 1/3 of the data will not be used. Now think about it. When I do with replacement, I'm going to double up and use specific data. I may even use a specific sample 3 or 4 times. Statistically speaking, 1/3 of the data will be left out with every data set. What we can do is that data is called out of bag samples. And while we build the model, we can predict at the out of bag locations. We can track that. In other words, we do model cross-validation while we build the model. It's all built in together. We'll talk a little bit about tree decorrelation. Let me demonstrate tree bagging right now. I've got one data set. I build a decision tree. Now look really carefully. Do you all see this? Look at the data points. Do you see they're different? Every one of these Bootstrap data sets are different. When I fit a decision tree, do you see the tree is different? Now what I do is I take the average of all those trees. What I did was I just took this value, this value, this value, this value, the same locations, I averaged them. I did it by hand and I built this. This right here is called tree bagging. averaging over multiple bootstrapped decision trees. Now, we can observe the impact on how many trees you use in tree bagging. First of all, one tree, that's decision tree. It's no different. 2 trees, 5, 50, 500, 5,000. Seriously, I should get a bonus or extra pay for that. That was really over the top. This, if you look really carefully, what's the difference? Okay, what is the difference with this tree right here? This tree bagging, you'll see that the model starts to become continuous. Now we can also look at what happens to model variance as we increase the number of trees. Now we can visualize that. The way we'll do it is all of these models use one tree. That's decision tree bootstrapped. Now we have 3 trees averaged, and now we have 1,000. What do we see? Do you notice how these models are very different? That is model variance. The difference is decreasing as we have 3 trees, and at 1,000 trees, it is stabilized. Model variance, you can visualize it being reduced through ensemble learning. Very powerful. Okay, let's introduce the concept of random forest. It's a very simple step from tree bagging to random forest. It goes like this. If all of your decision trees from bootstrapping are all very similar, this method doesn't work. In fact, the standard error calculation I showed assumes no correlation between all of the samples. Okay, so what are we going to do? We got to decorrelate the trees. The way we do that is through random forest. What we do with random forest is every time we're going to do a split, hierarchical binary segmentation to build a decision tree, we will say, yeah, you're only allowed to look at a subset of the features for the next split. Typically, we use a rule like this. You can take m number of features, the square root. So I have 9 features. I'm going to say that you're only allowed to use 3 of them. That's a typical rule people use, square root of the number of features. And so at random, you only consider a certain subset of the features. It forces each one of the trees to be very different. Your ensemble will be decorrelated and it improves the result. What's the result? If you look at the result right here, it's pretty cool. This is a random forest built with 100 trees, maximum depth of 5, 1 predictor selected for every split. We have 2 predictor features. You can only randomly pick from one of them. And the result is we get the very best model we built so far. Let's go ahead. I'm going to walk through this and let's go ahead and look at code. I think it's much more fun to look at code than for me to just talk about it. Let's go back to right here. And I have ensemble trees right here. I have another workflow right here. We have it up on the learning management system. And we'll run through this right here. I'll show you random forest and tree bagging. First comment I should make is that SCIKIT-LEARN ensemble module has a function, a bagging regressor and random forest regressor. So here it is right here. So that we're able to go ahead and run these functions. We'll import that. We'll import some convenience functions so we can visualize what we're doing, and we'll import our data set. This is the same data set we worked with before. So everything I did before, I'm repeating. So you'll notice I'm just going to run through it pretty quickly. We check the correlation matrix. We visualize the correlation matrix. There's some good information shared between the features, the matrix scatter plot. We've done this before. Let's go ahead and look at the distributions, training versus testing to make sure that we have fair coverage of the range of values for the features. And we look at this scatter plot right here to see how we're doing in the bivariate, the 2 features to predict the third, the color coding of the location map. Let's go ahead and start doing some ensemble learning. How does it look? Well, the first comment I'd make to the people who code all the time, let me say the following. Decision tree regressor will be used within a wrapper. The wrapper is bagging regressor. In fact, so what we'll do, and for everybody else, we're going to declare a decision tree with its hyperparameters right here. Then all we have to do is we run the bagging method, and we give it the specific model it should work with as an input. Now, what's really interesting is the bagging regressor right here. We just tell it work with this model right here, which was our decision tree. What do we learn from that? What I just explained to you, the tree bagging approach could be applied to any model. You could apply it to linear regression, in fact. That would not be a problem. So you can make any model, set its hyperparameters, and send it to this methodology. Let's go ahead and run that and take a look at it. Right here, we've done multiple bagging of the data set. You look at the data has changed. If you look very careful at the points, they've changed. And as a result, we got different models. Now what we do is we're going to go ahead right here and we're going to just average all of those models. I literally just took cell by cell or location by location. I averaged. I've done tree bagging by hand. Now, I've also did other demonstrations right here where I changed the number of trees and I demonstrated the fact that it goes from a very discrete model to a more continuous model. That last run, that's the 5,000 trees. Did you see how that got hung up? So here's the code right here to build a bunch of different tree bagging models with different numbers of trees. Okay, I'm going to skip ahead to demonstrating random forest right here. And I want to just show you the code is very simple. Random forest, the hyperparameters, we instantiate it. Then what we have is we'll visualize and take a look at the model, and we'll do a little check cross-validation plot right here. We'll see we're a little bit underfit. You can tell by the fact that we have this, what we call conditional bias, a little bit of a slope there, but we're doing pretty good for the model so far. We can also demonstrate right here that we can go ahead and do a check on the model's performance. Oh, sorry, right here. No, I just realized I'm really running out of time and I don't want to just skip through along here. I'm going to stop with just showing the random forest model. What I'll do right now is I see, Daniel, you've got a question right here. If after decision tree or random forest model, the predicted output fails to match the actual data, but shows a very low RMSE, so basically just a measure of the mean squared error or root mean squared error, or MAE, which is the mean absolute error. One is an L2 norm, the other one is an L1 norm, but both measures of error. Is it still considered as a good model solely because it's low error? Okay, this is a very good question. In general, we want to be careful about our models. The main thing is make sure we're doing fair train and test. Make sure that when we're calculating the mean squared error, that we're actually looking at data that challenges the model. In fact, is very similar to the ways that we want to use the model, the difficulty of that estimation problem. If we do that, I'm much more comfortable to go ahead and move forward with the model. At the same time, Daniel, keep in mind irreducible error and recognize the value of your model. Even if it has kind of a high error, it still is getting you closer to the solution. And you may have high irreducible error just because of the quality of the data, the level of the noise of the data, and so forth. If we do fair train test, I think we're in pretty good shape. Here's a question from Tyler. Okay. So this is a very good question here about data transformations and what I would call feature engineering, Tyler. You're asking about how do we transform and deal with the data up front. There are many reasons we do data transformations. One of them could be we have an expected distribution known from physics. Another issue is we might have issues with outliers and so forth, or closure. You're working compositional type data like grades where they need to sum to 100%. There's many, many reasons we want to do transformations. I spend an entire lecture in my graduate level course just talking about data transformations. Feature engineering is critical. In fact, probably 90% of the work. Today, we spent all of our effort around the 10% building the model. Okay, it's 2 o'clock right now. And I do apologize. I usually like to hang out and talk after these, but I do have to run and go meet with a company and talk about a collaborative project right now. I do appreciate the questions and everybody contributing, participating today.
Thanks, Michael. Appreciate it. Thank you, Michael. Is there anything else? I can close out the meeting.
Avi, thanks for your help today.
Yeah, absolutely.
Thank you very much, Fatima. Thank you for the questions and comments. Glenn, thank you very much for joining in with comments. We appreciate that. Daniel, thank you for your questions. Appreciate it. Good to see you again. I see you on Twitter all the time. Rodrigo? All right. Hey, thanks, everybody. Stay safe. Thanks a lot, Tyler. I appreciate your question. And hello to our Canadian friends. You heard me say Zed, right? Okay. Everyone stay safe. Okay, bye.
Thanks, Michael.